All right, so let's talk about line spectra and the experiments that help us learn more about the electronic structure of atoms. Remember, we can't actually observe electrons that surround an atom directly. They're way too small to do that. So, scientists, chemists, and physicists use experiments like the photoelectro effect and line spectra to understand the behaviors of electrons. And then eventually that comes to build our most modern day description of electrons, and that's the Bohr model of the hydrogen atom. So these experiments lead up to that model that we've developed. All right, so a little bit about line spectra. So let's think about the different colors of the rainbow that form from white light. White light comes from the sun. The sun or white light is a continuous spectrum of light. So what that means, continuous spectrum, means that it contains all the colors or many, many different colors, like of the rainbow. So that's a spectrum of light, that it contains many colors. That is different than the experiments that we did in the photoelectro effect, where we shot a single energy of light, a single wavelength of light, purple light. So purple light with that certain energy of light, let's say 400 nanometers, that is monochromatic light. Mono meaning one, chromatic meaning one color. So one color of light. So the photoelectro effect is involved with monochromatic light. This picture here is depicting white light, a continuous spectrum or many different colors of light. So we know, how rainbows are formed. White light can go through a prism and then it can separate all of the colors that make up white light into a rainbow. And so the reason that we see that rainbow that comes from white light is because of refraction or bending of light due to the different wavelengths of color. So, we said red light has a longer wavelength. Red light has a longer wavelength. Purple light, which has higher energy, has a shorter wavelength. All right, and so those differences in wavelength is what causes the refraction and the separation of white light. And then, after we take a prism, or if you see a rainbow outside, essentially tiny water droplets can be like little prisms, and that's what causes the rainbow to separate. We could even take another prism and put together back that rainbow and make it back into white light. So, how scientists use light to understand atoms and electronic structure a little bit more is through the use of discharge tubes. So, using a discharge tube is that tube is filled with the vapor of one element. So, in this example, we have a hydrogen discharge tube, so it's just a tube filled with hydrogen, and in this one, it's a tube filled with sodium gas, sodium in the vapor phase. All right, and so in this discharge tube, we supply some energy to it, and what happens is that the tube glows, kind of like a neon sign. And we've talked about this before. Neon signs is filled with the element neon gas, and we put energy through it to energize those electrons. And so what scientists observed in this experiment of discharge tubes is that depending on the element that is inside one of these tubes, they would see a different spectrum of light, and they would see specifically a line spectrum. Line spectrum is different than our continuous spectrum of white light. White light contains all of the colors of the rainbow, so that's like what you see here, white light. But when you energize a discharge tube of a specific element, that element would only emit certain specific wavelengths. So here's what we see with our hydrogen and sodium discharge tube. So you see here, let's look at hydrogen first. Our hydrogen discharge tube, when that tube's filled with hydrogen, we see these four different lines appear. And so we see, it's just those lines just correspond to specific components of the whole white light spectrum. It's not just white light, it's only these specific colors. So each one of these specific colors is related to a specific wavelength and a specific energy. And so you also see the sodium discharge tube has different lines than white light and the hydrogen discharge tube. So here we see different lines with different wavelengths, different energies being emitted from sodium. So scientists, physicists, chemists, they found it curious that each of the elements displayed a unique line spectrum signature. So each one of these lines corresponds to a certain energy or frequency, and scientists were able to connect the dots and come up with the Bulmer series, which is a way that we can describe those discrete lines that we see in a line spectrum. So let's look at hydrogen, the line spectrum for hydrogen. So most people will be able to see with their eyes visually 3 or 4 discrete lines on the hydrogen spectrum. So you see here that there's 1, 2, 3, 4. But if you actually did this experiment in lab, put up a hydrogen discharge tube, put that light through a prism, you might only be able to see 3 of the lines, because this last line is way in the ultraviolet region, and so it might be hard for your eyes to actually see it. But regardless, there should be at least 3 or 4 discrete lines. And so Johannes Bulmer was the one who came up with a simple equation that reproduced the frequencies of the line spectrum. Remember, each of those lines has a specific wavelength and frequency and energy. And so he came up with this equation to describe the energies of each of those 4 lines. So this is his equation that he came up with, that the frequency of one of the lines off of the hydrogen spectrum is equal to a constant that he came up with, and then in parentheses 1 over 2 squared minus 1 over n squared. So what is n? N is just an integer where n can equal 3, 4, or 5. So when it is equal to 3, 4, or 5, he was able to predict the exact frequency of each one of these different lines, like where n equals 3, 4, 5, and 5. All right, and so you see here you can input n as 3, 4, or 5 into this equation. So in this example, let's say n equals 3. So if we put frequency equals that constant times 1 over 2 squared, which is 4, minus 1 over 9, which is, that is just equal to 3 squared. You get that the frequency is 4.57 times 10 to the 14th second, inverse second, or hertz. So that is one frequency, and that frequency corresponds to one of the lines on the spectrum. So we can convert that. Yes, so what you can do is take the frequency that we just calculated and determine the wavelength. So that's what we can do here. Insert the frequency that we calculated for, what was this, n equals 3. Put that into our wavelength equation using the speed of light constant, and you get that the wavelength with this corresponding frequency equals 6.56 times 10 to the negative 7 meters, or 656 nanometers. So 656 nanometers is in the region of red light. So this frequency corresponds to the red line that is on the hydrogen discharge tube, or the hydrogen line spectrum. So using the Bulmer series, we can say that this line corresponds to n equals 3. And then you can do the same equation with the different n values, and you get that this teal line is n equals 4, then we have n equals 5, n equals 6. All right. So depending on what n value, what integer value you put into this equation, our Rydberg equation, you get each one of those different lines. So the important thing about the Bulmer series is that he just kind of guessed and checked and came up with this equation. He came up with the equation, but he didn't actually understand why this equation worked. So that took a little bit more time and a little bit more experiments to figure out why this equation works. Why do we have to do parentheses and 1 over integer values in order to, get the different frequencies? But the important part here are the integer values that we put in. Those integer values have interesting meaning in the context of electrons. And that brings us to the next part so I'll just, finish the story and how we came up with the hydrogen atom. So Bulmer essentially laid the foundation of the electronic structure that we today know of the hydrogen atom. He didn't understand why, but it took Niels Bohr to really fine-tune his equation and really understand why this works. And at the time when Bohr came up with the hydrogen atom model, or his model for the hydrogen atom, it was so profound that he earned a Nobel Prize in physics due to his interpretation of the observations that all of these chemists made through the photoelectric effect and the line spectra of discharge tubes. So let's talk about the Bohr model of the hydrogen atom. So let's just remember this is related to the integer values that we put in the denominators here. Those integer values have meaning. All right, so the Bohr model of the hydrogen atom is a detailed explanation of all of the experiments and observations that we just made. So there's two different postulates that we will cover that build the foundation of his model. So the first postulate of the Bohr model is that the electron is restricted to certain energy levels corresponding to certain circular orbits around the nucleus. Circular orbits around the nucleus. All right, so this first postulate kind of piggybacks on the Rydberg equation, where we put in those integers. So those certain energy levels that I talk about here are designated as integer values, or this n value that we call the principal quantum number. So n is equal to any positive integer. So n can equal 1, 2, 3, 4, and many. So typically an electron, when it's in its ground state or when it's in its lowest energy state, n equals 1. So an electron, you can kind of think of this as these energy levels as like floors in a building or rungs on a ladder. So you're in your most stable state when you're on the first floor, or if you're on the first rung of the ladder. So if you're an electron on the first floor or the first rung of the ladder, you have the lowest energy, and we call this the ground state. And so as n, those integers increase. So remember, an electron can only be in a energy level of 1, 2, 3, or 4, kind of like on a ladder. You can't go in between rungs of a ladder, or you'll just fall to the lower rung. You can only be in these specific integer value energy levels. So as n increases, or an electron is in a higher n value, the energy of that electron increases, and the energy of the electron increases, and so does the distance that electron is from the nucleus of the atom. All right, so as n increases, energy and distance increases. And that also makes sense with our ladder analogy. As you go up rungs of a ladder, you're increasing your potential energy, at least, as you go up higher and your distance is higher off the ground. So as n increases, distance and energy of that electron increases. So part of the Bohr model, and what made his contribution to science Nobel Prize worthy, is he came up with the equation to calculate the energy of an electron in a certain n energy level. So here is the equation for an electron in a certain n energy level. So remember, n can only equal 1, 2, 3, and etc. You can't have like an n equals 2.5 letter or number. You can't be on the second and a half rung of a ladder. You can't go to floor 2.5 in a building. It's only whole numbers. So this is the equation to calculate the energy of an electron in a certain n level. So energy of a certain level equals negative Planck's constant times the speed of light times the Rydberg constant, which is given here, times 1 over the n value, or the energy level of that electron squared. So you can kind of see how this sort of looks like the Rydberg equation, but there's more meaning to it now, because now what's the constant isn't just some generic constant that Rydberg came up with. There's also Planck's constant and the speed of light within it, so it has more meaning. All right, so if we just kind of take all of these constants because it is a constant, we can put that together and get that the energy of any electron in a certain energy of an electron in a certain energy level, which is n, so any integer, is equal to negative 2.180 times 10 to the negative 18 joules times 1 over n, that n value squared. So depending on what energy level that electron is, will change the energy, the absolute energy of that electron. And so what you see here if you put in the different n values, so if you put in n equals 1 into this equation, you get that the most negative energy you get is when n equals 1. So this is the ground state. So as you increase your n value, all right, so if you calculate energy for n equals 2, you see that the energy becomes less negative, or it has more energy to it. So if we calculate the energy of an electron in a hydrogen atom that is in the n equals 1 energy level, it should equal, so if you just put 1 over 1 squared, this whole thing equals 1. The energy of that electron is negative 2.180 times 10 to the negative 18 joules. So this is the most negative value that you can get within our integer values. So here, and this is also, we call this our ground state because n is equal to 1. So there is the energy for that single electron in n equals 1. So I propose a question here. What does the negative sign mean in this calculation that I just did? Well, it's not really a calculation. I just did times 1. What does this negative sign in our energy value mean? So negative, if we think about this in terms of thermochemistry, it means that when that electron is in the n equals 1 orbit around the nucleus, that electron is more stable. It's more stable in n equals 1 in that orbit around the nucleus than being completely separated from its proton. So the electron is more stable in n equals 1 than having that electron just not in an orbit at all, than having electron not in orbit or energy level at all. So it is more stable to bring the proton and the electron close together, where that electron is in an n equals 1 orbit around the nucleus, than it is to have those electrons and protons completely apart. So when you bring that electron and proton together, because remember they're oppositely charged, you get some energy payoff, that some energy is released because it is a negative value, so you can kind of think exothermic, that some energy is released. It is more stable when that electron and proton are close together. Okay, so let's talk about the second postulate of Bohr's model. So I already said that as you increase your n value within this equation, as you increase your n value, so maybe I'll write that, as n increases, energy also increases. But we already kind of talked about that with the first postulate. Energy becomes less negative, energy goes up. So we already said that energy increases. So when n does not equal 1, when an electron is not in its ground state and an electron is in n equals 2 or 3, we call this an excited state. So this is when n does not equal 1, is an excited state. So that electron is not in its ground state, it's in some higher level. So the second postulate here is when electrons absorb energy, I'm going to put this in parentheses, but jump to a higher energy level. They jump 2 levels further from the nucleus. So they jump to energy levels further from the nucleus. So essentially, multiple things happen when an electron absorbs energy. The first is that its energy goes up. Also, its n value will go up. That's the second thing. So its n value will go up, and its distance from the nucleus will go up. Distance from nucleus. But we already kind of talked about how all of those terms are related. As n goes up, energy goes up, distance from nucleus goes up. So that happens when an electron absorbs energy. So how does an electron absorb energy? Well, if we think about our discharge tube experiment, we're sending an electrical current through the discharge tube. So that is a way for electrons to become energized, absorb energy, so they jump up to higher energy levels. All right, so this is directly related to that discharge tube experiment. So when you put electricity through that discharge tube, electrons jump up. But what we actually see, those line spectra that we observed in discharge tubes, what we actually see is when the electrons fall back down. Electrons, I don't want to say want, but they tend to try to be in their lowest energy state. So when you energize an electron, it's going to come back down eventually, and eventually it's a pretty quick process on the order of picoseconds, or femtoseconds. And so that's what the second part here. So when the electrons fall back down to lower energy levels, they emit energy in the process. So this is in the form of photons. So this essentially shows this is our discharge tube experiment. All right. And so when the electron falls back down to a lower energy level, it'll probably go back to any lower energy level, n equals 1 or 2, whatever's lower. And so the difference in energy between those two levels that it fell from corresponds to the light that is emitted, or the wavelength or frequency of light that is emitted in the form of a photon. So there's two energy levels or orbits involved in this transition. So when electrons absorb energy, their n value goes up. When they emit light, their n value goes back down to a lower number. And so, yeah, the light emitted that we observe in those line spectrum from the discharge tube experiments are actually this phenomena happening, that those electrons are falling back down and releasing light in the process. And so you can kind of see this here in this schematic. So these horizontal lines are the different energy levels that we've talked about, n equals 1. So this is our ground state. And then these are all our excited states. All right, so this is n equals 2, 3, 4, 5, and whatever. So energy goes up as we increase our n. Also, distance from the nucleus increases. So you can energize, or an electron can absorb some amount of energy from its ground state. But what we actually see in the form of light or photons is when that electron comes back down to the ground state, or not always the ground state. So if you have an electron in n equals 5, it can go down to n equals 2, and so there's some light emitted there. Or you can jump between or fall between 4 and 2, or 3 and 2, and each one of those transitions from a higher to lower n value, light is emitted. All right, so maybe I will mark these. All the arrows pointing up, this is where energy is absorbed. And all the down arrows, this is energy emitted, but in the form of light or photons. So this is what we see. Right? And so if we look back at our hydrogen spectrum, we can actually assign each of these lines that we see to a certain emission transition between two different n values. So the red line that we calculated before, that energy is related to the transition between n equals 3 to n equals 2. So this line right here. So this line, that energy between those two energy levels is equal to our 650 whatever nanometer line that we see. What is it? It's actually 600. I'm not sure. What did we calculate it as? We calculated it as 656. I'm sorry. Okay, 656. All right, so it's this down arrow of emission relates to that photon that we see in its line spectrum, or we can more specifically call it an emission spectrum, because all of these downward lines are emission. So emitted or emission. Down arrows mean emission, up arrows mean absorption. All right, so what we should gather from this slide is that each one of these n energy levels corresponds to a certain energy that we can calculate with this equation. And it's the difference in energy between these lines that corresponds to each one of these different lines on the line spectra of the hydrogen atom, is the falling of one of these electrons between these energy levels. And so it's the difference in energy that makes up the energy of the photon that is emitted. So we can actually calculate the photon that is emitted when an electron changes orbitals or changes energy levels around the atom of the nucleus. So we can calculate it. All it is E final minus E initial. This is the energy of the photon that is emitted. So it's E final minus initial. So it's it's N final and its initial, or sorry, yeah, its final n value and its initial n value. All right, so each one of these energies can be calculated using that equation above. So we can actually combine that equation to include uh, both of these n values because they will be different. And typically, when an electron falls in its orbit, its n initial will be larger than its final integer value when an electron is emitted because it's falling, right? It's falling from a higher to a lower energy level. So falling. Right, so we can put together an equation that includes both of those n values. So we're essentially just combining the single energy level energy above, combining it into one. So you see we have that same constant that we saw above, all times 1 over its final energy level squared minus 1 over its initial energy level squared. All right, and so like I said, if this energy, if an electron is emitted, or the if an electron is emitted, so that's what I have here, emitted, or its initial value is larger, its initial integer is larger than its final energy level, then the change in the energy of the atom will be negative. So again, let's think about what that negative value means in terms of energy. So if it's a negative value, that means energy is being released, like an exothermic reaction. So which direction is energy going? It is, I guess, going out to surroundings. So this makes sense because an electron is emitted in the form of a photon. So since a photon is being emitted, energy is going out into its surroundings. So that's related to there. That's why we call it an emission spectrum, because energy or photons are being emitted. All right, and so we can calculate the energy of that emitted photon. Just calculate it. So essentially, we can just ignore the negative sign because that negative sign just tells you the direction energy is going. So we can calculate the energy of the photon using our equations, right? Hc over lambda, right? So you can calculate the wavelength of your photon using this equation too. Right, so essentially ignore, once you do the calculation of a emitted electron, so that electron is going from a higher to a lower energy level, you should get a negative um, energy change of the atom, but that is equal to the opposite. Essentially, it's a positive energy for the energy of the photon because that photon's being emitted. So that's why there's a negative sign on our delta E energy of the atom. And then we can go ahead and calculate the wavelength of that photon. And those wavelengths should correspond to the colors that we see on the hydrogen line spectrum. All right, and so we can then go ahead and simplify things a little bit more by putting things together, right? We can set this equal to Planck's constant, speed of light over lambda, or energy also equals Planck's constant times frequency. All right, so we can set up a new equation here, right? The energy of the photon is equal to h times the Planck's constant times the frequency of the photon. So that is equal to the negative of the energy of the atom. So this becomes a positive constant times the 1 over your final and initial energy levels. All right, and then just do some math manipulation to just kind of isolate the frequency of the photon so we can calculate it. All right, and so h is Planck's constant. It's a constant, so this becomes a new constant. All right, this on the outside of our energy levels here, and then you see that the frequency of the photon equals 3.29 times 10 to the 15 per second. So that is this constant divided by Planck's constant. So if this number looks familiar, it should, because this is the same constant that Bulmer found experimentally decades later. So now we're just giving more meaning to his constant because we found a factor of Planck's constant within it. So we can see that his calculations with those experiments actually they work out. But the reason that Niels Bohr got the Nobel Prize is because he explained why. And if you remember the Bulmer series, that equation, you saw that this first term was 1 over 2 squared, that first term. So that means what he was calculating was assuming that the final energy level was the second, n equals 2. N equals 2. So what this means in terms of our line spectrum, if we go back up to our line spectrum for hydrogen, up here, right? So all of these lines that you see in the visible region have electrons falling to not the ground state, but to the n equals 2 level. That doesn't mean that photons aren't being emitted that are falling to the ground state. It's just what we can see are electrons that are falling to the second energy level. So from higher energy levels to just the second. So what we are seeing in these 4 lines on the hydrogen spectrum correspond to these different transitions from 5 to 2, 6 to 2, 5 to 2, 4 to 2, and 3 to 2. That these lines are all terminating, or that their n final is n equals 2. And so that kind of gives a little bit more meaning to the Bulmer series that he came up with experimentally to describe the line spectrum of hydrogen. All right. So, really, what you should be able to get out of this, what I could test you on is, giving you different n values. So, a final and initial. You should be able to calculate, given this equation. I will always give you this equation. um, the energy of the photon that is emitted. So that will require you to identify what is your n final, what is your n initial. Can you put it within this equation and calculate from that the energy of the photon and then either the frequency or the wavelength, depending on what the question asks. So all you really need, because all of these, H, C, all of those are constants. All you need to figure out the wavelength or frequency of an emitted photon is your initial and final energy levels that electron is transitioning between. All right, so that essentially summarizes the Bohr model and how we understand electronic structure. That electrons aren't just, flying around the nucleus of an atom. They actually reside in very specific orbits around the nucleus. So those orbits, we will expand on those because it doesn't stop at the Bohr model. This is more of a modern approach to atomic theory and atomic structure. So there's a little bit more detail that we have to get to. So Niels Bohr didn't get all of the details, but he got a lot of them to have us understand how electrons behave and how that relates to the observations that we see in the photoelectro effect and in the discharge tubes. Okay, so to get into that, the details about the atomic spectrum and more details about the specific energy levels that electrons can reside in, we need to kind of uh, uh,